All right, so here we go. So basically, I think we started this problem here, which is a symmetric cross section, but with a C shape. Okay. And what was different about this one is that this one was subjected to a moment that was at an angle. So meaning what? That it was an angle in this direction, but also an angle on the other reference frame. No, over here. So basically, we have this. That's fine. We have this, so that's what's creating two different moments. Okay, not only just a combination of both moments. One about the z-axis, and another one about the y-axis. Okay, so these two components, and we started to talk about the section. Okay, about the properties, and we stopped at the point where now we need to find the area moment of inertia. So we need to find what? The area moment of inertia to see at the bending in this axis, up and down, and then we have to find the IY to look at the bending in this direction, since we have moments in both MY and MZ. Okay. Somebody asked me, I think yesterday, what was the meaning of the IXY or different or stuff like that. It's not a straight answer, but if you want, I was thinking about it. It's not 100% true, but if you want to think about it, if it really is related to bending about one axis, and this one is the two axes, so you can say that the IXY would be related to what type of motion, probably more related to the rotation, no? Yeah, does that make sense? Even though the J would be the summation of the IXY plus XYZ. All right, so I think we stop at the moment of inertia. So let me redo that figure, that little figure over here very quick. So I think I say at the end, you can model this like having, let's say, one flange on top, one flange at the bottom. You have this. Oops. There? I don't see. Okay, because I don't see. I don't even see on this screen because of the light. So I think we call these two areas here A sub 1. A sub 1. Correct me if I'm not correct. Okay, and I think this one here was A sub 2. Did we calculate the location of the CG? I think we did. Yes, correct. So basically we are here. So we can say here the center of gravity would be here. Yeah. Okay, so this will be here the z-axis. Okay, and we had the equation, let's say for the parallax term, I wrote I equal to I plus A d squared, where d is the distance. So this is what is known as the parallel is the image better or not? Yeah, and let me know, because if not, as far as you can say, change the overhead projector, okay? Yes. Yeah. But let me know if the image goes out of the screen, because I cannot see. Okay, so the goal now is to calculate I see. Okay, so this will be equal to what? So basically, now, if we have this element here, this area here, this area, okay, we also have an axis about itself, no? Okay, so what is the, by definition, I'm going to put it here. Let's say this is B, this is H. What is the moment of inertia of this one about the z-axis. I mean, I'm not going to put too much detail, but it would be 1/12 of what? B h cubed, no? Yeah, that's the general definition, okay? So using this one, what would be the area for this one? Let's see what were these dimensions. If I remember right, this was B flange. The thickness here was the flange. And this is the web properly. And then this distance here will be d/2. But it's not the same d, okay? I'll move it here. Okay, so what is the role of the parallax theorem? Is to move the area moment of inertia of one point or one area if you want to a different location. Okay, so what is the area moment of inertia of the surface A1? What would that be? Would be 1/12. Or what? What would be the base? I mean, but let's just use the letters. I think it's easier to understand. Would be BF times what? T sub F flange to the cube, no? But that is the moment of inertia about the own axis of the area. We don't want it about here. We want it about the z-axis, no? So in order to move this one to here, what do we use? The parallax theorem. So now this would be equal to what? What is the area of that little element over here? The BF, no? What would be the distance? Okay, so d/2 minus d flange/2 if you want to be accurate. And this should be squared. Okay, sometimes you do that in, I mean, here you're not aerospace. In aerospace engineering, I think we're talking a little bit about that at the beginning of the semester. What is one assumption we have been doing all the time throughout this semester and you have been doing in solid mechanics? Members are long and slender, no? Okay, so if you want one approximation, would just be to take the d/2 and forget about the thickness, no? Okay, would be an approximation, but since here we're doing that way. Now, so this will be for what? This will be for this area. Will it be different for the one at the bottom? It will be the same just because the distance is squared, no? So I can multiply now this one by 2. Okay? Remember, in class, ask as many questions as you want. Now, we need to find the moment of inertia for, so this will be, so this is for A1, okay? Now, what would it be for A2? What would be the moment of inertia for A2? This time, what is the value of the base? Okay, T of the web, no? TW. What would be the height? So D, so the whole thing, minus twice the thickness of the flanges, no? Because it's one on top, one at the bottom. I mean, it's correct, okay. And this will be cube. Do I need to use the parallax theorem over here? You can use it if you want, but what would it be? Will it be this area times, what would be the distance? 0, so you don't need to use it, no? Or if you want, you can use it, but you'll find out that D is 0, so you don't need it over here. So basically, this will be for area A2. Any question? Okay, let me know if I will go out of the page, no? Yes.
Isn't the distance here? It's like it's along the z-axis. It's already been symmetrical on that.
Basically, remember, what is the meaning of IZs? How likely is one surface or this element to rotate about this axis?
Okay.
Okay, remember the definition, no? Because now that we have done IZ, okay, so I give you the value after the substitutions. If you substitute by the values, I have the value here. That gives you, this should be equal 11.314 10 to the 6 millimeters to the 4. Okay, so remember the I is resistance to bending about one axis, or resistance to rotation about one axis. Okay, so this one is about the Z axis. Now, let's say we want to calculate the I sub Y. So I sub Z, we come here, I sub Y. So now we do the same thing, but instead of looking about how unlikely it is to rotate about the Z axis, we're going to look at how unlikely it is to rotate about the Y axis. So you might have to be a bit careful, because what was the distance? What was the Z bar that we had? I think Z bar was that distance here. So Z bar equal to 14.5. 14.65. Okay. And do you have over here the data for the BF? How much is the width of the flange? 58.44. So that means that if we look at the CG, it's not going to be at the right location, but if you look at the CG of this, it should be somewhere more, let's say it's here, no? I know it's not in the middle, but it should be in the middle, no? But it should be past the Y-axis. That's what I'm trying to say. Okay, so now we're going to see how these surfaces here, A1, the two A1s and A2, are unlikely to rotate about this axis, no? Yeah? So we're going to do exactly the same thing. So let's start by A1. This time, what would be the area of this one over here, of the top one? Would be 112, but this time, what would be the value of the base? Be careful. Now you need to switch this, like if you want, like this, no? So what will be the base? This time will be T of the flange, correct? Yeah. What will be the height? DF cube. But this will be about which point? This one over here, no? Yeah. About the CG of this area. So what do we need to use? We need to move it to the y-axis. So we use the parallax theorem. So what will be the area? This should be unchanged. Should be what? BF times TF. But now be careful. We need to find what is the distance over here. So what will be the distance between the y-axis and the CG of that element here? Or the other way around, could be the other way around, okay, because it's square anyway. So it will be BF over 2, no? Half, that will be the location of the red dot, no? Minus Z bar, or you can do the other way around, because it would not matter, because this value should be what? Square, no? Okay, once again, is it going to be the same for the other surface at the bottom? Yes, so we can multiply this by 2. I don't have space to do it here at the before, so this time I do it next. So again, this should be for A1. Yes, times 2. Just put 2 if you want, I don't know. Whatever is easier for you. Now we do the same thing for this one over here, for the A2. So that would be equal to what? So 112. Okay, so the base will be D minus, what do we get before? Minus 2T. What? Can you say W, but it should be W, no? The BF. So that is now the base. What should be the height now? The TW cube, no? You see that? Like, I mean, if it's easier for you, just rotate this, no? Okay, this is the base, this is the height, no? Okay. So do you need to use the parallax theorem? Yes, because this one is about this axis in the middle. We need to move it to the y-axis. So what is the area of that one? It's a bit more complicated. The area will be D minus 2TF times TW. That's the area. And what will be that distance from the middle of this element to the y-axis? What will be that distance over here? Okay, yeah. Or we could say will be Z. I think it's the same thing you were going to say. You can do either one. Z minus half the thickness of this one, no? Yeah. Minus T web divided by 2. Squared. Again, over here, if you simplify and you just put Z, it will be fine with me, okay? Yeah, I don't see it. Okay, and this will be for A2. Okay, so if we do the calculation, this should give you I sub I equal to 0.70222 10 to the minus 6 millimeters, oh, 10 to the 6, sorry. 10 to the 6 millimeters to the 4. Okay, so remember, we are doing all this stuff in order to do what? We need to calculate the stress, no? The stress is equal to what? Sigma equal to M Y divided by I, no? So we got the M's, we got the I's. Now we need to find what is the location, if you want, the Y and the Z for the 2 points where we need to calculate the stresses, which I think were a point right at this corner and another point right at this corner over here, no? Okay, so let's just do that next. So location of H and K. Okay, so let me just do here. Quick sketch. Okay. Generally, I would do it without the thicknesses, but anyway, it's so we know, let's say this would be, this is Z, this is Y, this is point H, this is point K. Can you see? Yeah. So, yes. Yeah. I mean, I think we should do this table here a little bit bigger, but we're not going to change it now. Okay. So, what were the distance for, let's see, for these 2 points here? I think that distance here, we call it d/2, no? Yeah. So what would be the Y location? So let's say for point H, y will be equal to what? E over 2, correct? And let's do the same thing here for point K. For here, point K. So for K, the y will be equal to what? Negative E over 2. Now, what would be the z coordinate for point H? So will be no, because it's going positive in that direction, no? So will be z bar, which is the 14.65. And then what would be the z? So this time, yes, should be negative. What would be the z for this one over here? Which one is higher? BF? I think it's BF is higher, no? But I mean, it should be negative, no? So I think this is BF, no? So I think it's Z minus BF. So it's negative, or
Yeah, that would be negative.
I mean, or you know, or you need to know that it's negative, okay? So let's say Z bar minus BF. If you want, just give me the values. That way there would be no ambiguity at all. So what was D? So 178 divided by 2. Z bar is 14.65. So this would be minus 14.65. And this would be 14.65 minus, how much is BF? 58.4, okay? Whatever these values are, but that way you know that it's negative.
Why is the y for K negative 14.5?
Sorry, no, this should be minus 178 divided by 2. So I was going too fast. Thank you. Okay, so now we have everything in order to calculate the bending stress. Okay, so let's say here now we can calculate the bending. So let's say here, we call in the expression for the bending stress. Okay, so in this case, remember, it will produce a stress on the S direction. I'm not going to put the sign, so one would be mz times y divided by which one? Iz, perfect. And here I'm going to put here plus yc divided by iy, no? So remember here, I told you before, time to be determined by inspection. I don't want you to apply one equation straightforward. So you remember what would be the sign? If his intention is positive, if it is in compression, it will be negative, no? Okay, so because this really the first one should be negative, but that's what we see over here. Okay, so let's first look then at, let's say, point H. This is the difficult part, okay? This is understanding. So point H, let me just do very quick and a little sketch. Here we add, let me do it here. I'm not going to do the thicknesses anymore because they aren't really that important. So we have this. We know point H is located over here. We know we have here the y-axis. And this should be the z-axis. What do we have for my and mz at the first page? Okay, so both of them were positive. I think that matters. So we had mz equal to 4.87 kilonewtons per meter, and my equal to 1.126 kilonewtons per meter. Okay, so what does that mean? If it's positive, it's going to go counterclockwise. So if you think this would be my, and this should be mz. So at point H, due to mz, we'll do that in a minute. And let's say here at point H, due to my. So if you remember, if something is bending, let's say this page is bending this way, is the top in tension or compression? Tension, and the bottom will be in compression. Okay, so that's what we're looking at now over here. Point H. So let's look at the mz. What would it be? Well, how would that be then? Here we are moving about the z-axis. No, we're looking about the z-axis first. So bending this way. So this will be curving due to this will be like a smile, no? It will bend this way, no? Yeah. Where is point H? At the top or the bottom of the page? Top. So it will be what? What did we just say? The top is tension, bottom is compression. Here we say this will bend this way. So point H will be what? Compression, no? Okay. Compression, or if you want, should be negative, whatever you want. That's why here the values are not that important. What about my? How this will be bending? It will be the same way, no? Yes? So what should be then H, tension or compression? I mean, don't look at me, you should be the one looking, so it should also be compression, but can you see that? Okay, so this is the difficult part here. So, okay, so at the end, what are we gonna have? We're gonna have sigma sub x should be equal to mz times y, and here be careful because times I sub z plus my z times I sub y. So what we just said over here is that this term is in compression because I don't want you to get messed up now with the signs. Okay. We are looking at the whole term, no? Both terms are in compression, correct? Okay, so what would be the result right here? What do we have for MZ? 4.87. I'm going to do 10 to the 3 to move to newtons, no? What is Y? Y, just give me the magnitude because we don't need about the sign. So what was Y? I think we said was D over 2, no? I think here I have a value of D, I think is 17.8 or 178. 178 millimeters. So so how many meters would that be? 0.178 divided by 2. Divided by IZ. So IZ, what was the value for IZ? 11.314 what? 10 to the 6. Well, be careful. 10 to the 6 what? We want to move that to square meters. No, to millimeters to the 4th. So we have millimeters to the 4th. We want to move that to. Well, what would that be? 12 decimal places. So we have to, if we are at 6, we're going to go to -6. Is the change of units, okay? Yes.
Going back to finding the Y for the final page.
Finding the Y for final H. So it's this page here.
Yeah.
Yes.
It was it's 178 or it's 0.178.
Okay, so 178 here. So this is we have here. Let me put it here. We have D equal to 178 millimeters equal to 0.178 meters. No, it's fine. And the same thing we did with this one. Okay, here we had I sub Z is equal to 11.314 10 to the 6 millimeters to the 4. This is equal to 11.314 10 to the -6 meters to the 4. Okay, and we do the same thing for the IY. So what do we have for IY? I think IY is 0.7022 10 to the 6 millimeters to the 4. So it will be 0.7022 10 to the -6 meters to the 4. Basically, you understand how to do this. How do you go from meters to millimeters? So from millimeters to meters. 3 decimals. So you do that times 4 because it's 1, 2, 3, 4. No? Yeah. Oh, so you go All right, what will be the second term? Plus, I'm going to put, okay, so I don't know how to do this. If you want to put here minus, and here put a minus sign again, because both should be negative for compression. So what do we have for MY? 1.126 10 to the 3 times, what do we have over here? Times Z. What is Z? 14. So will be 0.01465. Divided by 0.7022 10 to the negative 6. So this gives you a value of minus 61.8 10 to the 6 newtons per meter square, which is the same as minus 61.8 megapascals. Yeah, so 1 Pascal is what? Newton meter square, no? Yes, yes. Let me know because I don't see it so. Okay, so here you have two choices to put these results. Either you put it that way, or you could write what? Or you could write what? Correct. Or you could write this is equal to 61.8 megapascals, but then you need to let me know that this is in compression, okay? So the negative side means compression. Okay, now we do exactly the same thing for 1K. For exactly the same procedure, point K. So if you want, I do again a quick figure here. I mean, but this one now should be pretty straightforward because this is point K. Z and Y. Let's see what I got over here. Okay, so sigma. All right, let's do it a bit differently here. At point K, due to MZ. At point K due to MY. I mean, what will be the answer this time? Both in tension, because if this side is in compression, this one needs to be tension, no? Yeah, or if you want, you can redo the whole thing again, but it will be tension. Basically means positive, and tension, which basically means positive. So we have exactly the same equation, which is MZY divided by IZ plus MYZ divided by IY. So, okay, let's put the value since we did it for the other one. So what do we have for, we can just copy the one would be 4.87 10 to the 3. What would be y? Should be negative over here, but we're going to take just the magnitude, no? So it's d over 2. What did we have before? 0.178 divided by 2. Divided by 11.314 10 to the minus 6. Plus 1.126 10 to the 3. Divided by the 0.70222, I think, 10 to the minus 6. But now we needed to be careful here. What is the value of the K for the Z? We say was equal to BF. What was the value for BF? Is it 584? 58.4, so it will be what? 0.0584 minus 0.01465, I think.
Does it matter that they were negative?
That's what I'm saying. Be careful here, because if you put the negative, then this will tell you what? That this term is negative. And if this term is negative, what does that imply? It's compression, but it's not compression. That's why I'm here. I'm not asking you to put the signs based on the sign of the moment or the Z, but by understanding. Do you see that? So don't make the mistake to do all the reasoning. This is going to be compression and then change the sign because the Z or the Y are negative. Okay.
So would it be best to just take the absolute value?
Correct. Just take the absolute value. That's basically what we're doing. That's basically what. Okay. This one?
That was supposed to be a negative.
Yeah, but what just say about it? Okay.
We take the max.
We just say, yeah, it would be better just to take the absolute value. So why? That way is negative? No, that way should be negative. Yeah, but we want to take positive. We want to take the absolute value. Remember, we are finding the sign by looking if it's tension or compression. So we are talking about the whole term. Do you understand what we are discussing here? Everybody? Yes? Okay. So both should be positive. So if you do the calculation, this gives you sigma x equal to, I have here 108.4 megapascals. Okay, so the last thing we need to do in this problem is to find location of neutral axis. So if you remember, I mean, you don't need to remember, you need to understand. I always say studying is not remembering, it's understanding. So what's the definition of neutral axis? Correct. So neutral axis, location where stress due to bending. So in this case, we have this will be equal to 0, no? Yes? Okay, so you don't need to remember any equation. So if the stress is equal to 0, we can rewrite the same equation. We have mz times y divided by I sub z plus my times z divided by I sub I. Okay, if you do some basic algebra, you find y over z equal to I mean, really should be a negative sign. No, don't worry about the negative sign. The real equation is a negative sign over here, okay? But basically, you could just take the absolute values if you want. So it should give you my IZ, MZ, IY. If you want here, just put the positive sign and say here, making no, here's important. Sorry for that. Here the sign is important, however, because it's going to define the rotation. So you need to put the negative sign here. Never thought about this stuff. Okay. So if you remember the other day, we say that when we did the derivation for all this equation, we say this is Y, this is Z, and we call this beta. Say that Y over Z is equal to tangent beta, which will be equal to negative MY IZ MZ over IY. Yes, yes, sorry. Okay, so if we do the numerical substitution over here, we're gonna get tangent beta is equal to negative 1.126 times IZ 11.314. I mean, you can put the, what is it, 10 to the 6 or 10 minus 6. Doesn't matter, 10 to the, what do you have, minus 6. Because it would cancel anyway. Divided by the 4.87. Yeah, the other moment. Times the 0.70222, I think 10 to the minus 6. So this will give you that beta is equal to minus 74.95. Okay, so if in an exam I ask you to find this location, I will give you the correct equation, okay? Instead of having to do with the thinking. Okay, so what does that mean? What does that mean at the end of the day? So if we do a figure of the cross section, so this is our original cross section where we had 1, 2, 3, 1, 2, 3. So we had this being the z-axis, this being the y-axis. What does that mean? That if I do here this line here from here to here to be beta, so that would be negative. It's going on the negative side. This would be the location of the neutral axis. So what does that mean? From this line, what should be the stress? 0. So what happened? If we only had, let's say, MZ, what would be the location of the neutral axis? should be there, no? If we only had MY, neutral axis would have been located over there, no? But since we have a combination of both of them, it's going to be located somewhere between both of them, no? Okay, so if you want, I don't do that in this class. I don't think it's, which one is the one at the top? K or H? H and K. But you can actually derive another equation from here, from what you, if you just take the vertical distance, you can calculate the direct stresses, no? Okay, but anyway, we don't do that, okay?
Why is beta measured from the Z axis?
Basically, because the symmetry is about this line. Okay. But what's important over here, most important over here to understand is that the location, put that in blue. What does this sign mean? You pass your driver license. Rectangular sign means attention, no? Okay, so attention. So what's important is what? What we just discussed is that the location of the neutral axis depends on what? Does it depend on the geometry? Well, a little bit, but it depends also on what? It depends on the loading. So a cross section can have different neutral axes depending how it is loaded, no? It's not like the CG that is not going to change no matter what, no? Okay, so that's what we're going to write. So the location of the neutral axis depends on the cross section geometry, because we had the IY and IZ, but on the loading, which is in this case MY, MZ, as well. Yes. Yes. So the CG, the position of the CG does not depend on the loading, no? No matter what, it's going to be located at the same location, no? Okay. But the neutral axis change because of the loading, no?
When you say we work dependent on really aren't changing that much, but
Moment of inertia are not changing on a cross section.
right.
Okay,
So,
it's a constant, yeah.
well, I mean, like with different cross sections, the moment of inertia with
I mean, they might change a lot. Okay, if you, I mean, imagine is if you make it longer, this one, how unlikely is going to be to rotate? The value is going to be much smaller, no? It will be much likely to rotate, no? If you separate from this one.
But I'm just saying it's more practical to change the load rather.
Depending on what is the minimum. I mean, let's say what is your constraint. Let's say you have a design where, let's say, the applied forces or applied moments are constant, so you can only play with the geometry. If it is the other way around, then you can play with the forces. No, I'm not going to say easy or not easy. It depends on whatever you want to use as for your design. Okay, for your constraint. Okay. So since we have time, I don't think I'm going to put that on the video. So let me stop the video. Let's talk a bit about the assignments. We have time. So stop recording. All right. So, oh, I need to leave this. No, I don't think I need to leave this. So I've had 3 people yesterday come into my office. So let's say the people that came, you were doing good. The procedure was good. Okay. And you were doing good basically on the bending, the shear and bending moment diagrams. But I think I recommended to the people that came to